Hello, my dear students. Welcome to this next session on industrial metallurgy. The module that we are covering at the moment is called alloy systems. These are the contents that we'll cover in session number 10. So let's get started. We are discussing here the unary phase diagrams. We would briefly discuss as to what is meant by these diagrams, and importantly then we'll check uh, by taking an example of a unary phase diagram that after it has been constructed through one of or more of the experimental methods, is it absolutely correct or not? And we'll do that with the help of utilization of the Gibbs phase rule. Okay. What is a unary phase diagram? Any phase diagram which is drawn for a pure substance for a one component system is a unary equilibrium diagram or a unary phase diagram. And as I said in the last session, for a pure substance, for a one component system, composition is not a variable. So the two variables that generally would affect the phase relationships in a material system are temperature and pressure. So unary phase diagrams are graphical representation of uh, what different phases are present in a unary material system under different conditions of temperature and pressure. Temperature generally would taken along the y-axis and pressure along the x-axis. So here we see unary phase diagram for one of the most important elements that we make use of in the industry, that's iron. Uh, you can see that in this unary phase diagram there are a few single phase regions. Here we have alpha phase present in iron, so this iron is called alpha iron, or the phase is called alpha phase. Then we have this epsilon phase, we have this gamma phase, we have this delta phase, we have liquid phase, and we have this gas phase. So in all we have about 1, 2, 3, 4, 5, and 6 single phase regions. Then all these blue lines here are two phase boundaries or two phase equilibrium lines. So if the temperature and pressure of pure iron is such that it falls, the temperature composition point falls on any of these lines. For example, if I put the cursor over here, the red dot here, if pure iron is put to a temperature and pressure represented by this temperature composition point, then iron has got two phases in it, a mixture of alpha phase and gamma phase. So there are so many different two phase regions present in iron. And similarly, there are some three phase regions also. There are two three phase regions, or you can say triple points in pure iron. One is point G, which comes under these conditions, and the other is represented by point B, which happens to be at this temperature and pressure condition. So now let's check the accuracy of phase diagrams. As I said in one of the earlier sessions, that we have to check for every region. Now here for illustration, for each type of region, each type of region means we have three type of phase regions in the pure iron's equilibrium diagram. We have some single phase regions, we have these two phase regions, and we have these triple points. So there are three cases. Case one, when there is only one phase. Case two, when there are exactly two phases present in pure iron. And case three, final case, when there are exactly three phases present in pure iron. Now when we have this in this one component system pure iron, when we have just one phase, for illustration I have taken that let pure iron be present at a temperature composition point Y, when it has got temperature Ty and pressure Py. Now if I ask the diagram, how many degrees of freedom do you have with you? You remember that when we discussed degrees of freedom in one of the earlier sessions, we discovered that here in this region, in this single phase region, I can change the pressure independently, I could have changed the temperature independently. Both are acting as independent variables which can be varied and would bring about no phase changes. So both are degrees of freedom. So the answer for degrees of freedom, which comes from the diagram for this region, is 2. Now, if I apply the Gibbs phase rule over here, Gibbs phase rule would be P plus F is equal to C plus 2. So if I apply P plus F is equal to C plus 2, how many phases do I have in this single phase region? I have one phase. I'm looking for the answer to degrees of freedom. It's a one component system, pure system, and there are two external variables, temperature and pressure. What is the answer for F? The answer for F comes out to be 2. From the Gibbs phase rule. For this region, the answer from the diagram also had come out to be F equal to 2. So for all other single phase regions also, there would be like this parity between the parity between the results of degrees of freedom coming from the diagram and that coming from the Gibbs phase rule. Now let us check the two phase regions of the diagram. Now when in this single component system we have exactly two phases, you can see, as we discussed in while we were discussing degrees of freedom, suppose the point is being represented by the temperature composition point Z, where it has got temperature Tz and pressure is Pz. Now suppose initially I wish to change the value of temperature from Tz to Tz dash. Now I have done that through my own discretion. I have changed the value of temperature independently. But the care that I have to take is that if the temperature value is changed this much, to remain in this two phase line so that the phases do not change. See, at point Z, there were two phases existing in the system, the alpha phase over here and the gamma phase from here. So now, so that by changing the variables, I do not change the existing phases, I have to remain on this line AB. And to do that, if I have changed the temperature value by this an amount, the pressure value ought to be changed by this an amount, so that this Z point shifts to point Z dash. So here temperature has been exercised as a degree of freedom, but pressure had to be changed. And this pressure change was dependent upon the amount of temperature change that you had made. Suppose if you had changed the temperature value from this to only this, then you would have changed the pressure value by this an amount. So you could exercise 1 degree of freedom. Either you can change the value of temperature independently, but then pressure change would become dependent on the temperature change, or you could have changed the pressure value by yourself, but then if you had done pressure changes according to yourself independently, then the temperature would have become dependent on the amount by which pressure would have been changed. So when for a single component system you are in a two phase region, there is only 1 degree of freedom. You can exercise that degree of freedom either in terms of temperature or in terms of pressure. So for two phase region, our answer from the diagram is the degrees of freedom is 1. Now if for that same two phase region I apply the Gibbs phase rule, from the Gibbs phase rule, I'll see that P plus 1 is equal to C plus 2. And when I put the value P is equal to 2, F will come out to be 1. So there is parity between the results. Similarly, when I go to the third type of region, the three phase region, you'll see that this triple point, when there are three phases, delta, liquid and gamma coexisting in the material system, or if I come to point B, which is the other triple point or the other three phase region, these both triple points have occurred at a unique value of temperature and pressure. And if any of the parameters, temperature or pressure, are changed, the triple points would be lost. So for both these triple points, or for any three phase region in the single component system, because you cannot vary the value of temperature, you cannot vary the value of pressure when you are existing at some particular triple point, right? The see, somebody can say, sir, if I come from B to G, see, when you come from B to G, the number of phases though are remaining the same, but the type of phases has changed. So the definition of degrees of freedom is that it should not result in appearance of any new phase or the disappearance of an already existing phase. So if you talk about this triple point, the three phases are epsilon, gamma, and alpha. And you cannot obtain this combination of these three phases for any other value of pressure or temperature. So there is 0 degrees of freedom. So diagram says that when you are at any triple point, the degrees of freedom are 0. And even if you find it out using the Gibbs phase rule, P plus F is equal to C plus 2, when you will put P equal to 3, F will come out to be 0. So there is complete parity. So what we have seen is that for all different types of regions that are existing in this equilibrium diagram, when I find out the results for degrees of freedom from the diagram and then from the equation Gibbs phase rule, there is complete parity in the results. So this diagram is absolutely correct. And that shows the application of Gibbs phase rule also. And this shows that our pure iron equilibrium diagram drawn with the help of experimental methods is absolutely correct. Thank you so much for watching.